this is Himabindu, Assistant Professor in IARE College from the Department of CSIT. So today in this video, I would like to explain about the Deterministic Finite Automata. So it is a finite automata model which comes from the without output in the finite automata. So we'll discuss into this discriminate finite automata. So here, before going to the discriminate finite automata, so we have to analyze what is meant by finite automata. So it is a finite automata is an abstract computing device. It is a mathematical model of a system with the discriminate input, output and the states, set of transitions from the state to state that occurs from the input alphabet. So here the finite automata is an abstract computing device. So, and it is a mathematical model of the system with the discrete inputs, outputs and transitions, set of transitions. So here in previous video we discussed about the finite automata. So with output and without output. So here we are saying that it's a mathematical model which comes from the discriminate inputs, outputs. So here we are specifying the outputs. So here, so finite automata with output we have two models and without outputs we have three models. So with the input, so with output we have a Murray and Millet. So these are the two models which comes from the finite automata with output. And coming to the without output finite automata, we have three things, three models. One is DFA and second one is NFA and epsilon NFA. So these are the three models comes from the finite automata without output. So this is the main definition of the finite automata, and we have finite automata we have to represent in the form of three things. So one is a graphical thing, and second one is the tabular form, and third one is the mathematical. So here the graphical representation is here represented as a transition diagram. So in this transition diagram we have states and actions, and also called as transition function, transitions. And this graphical representation we have two parts, one is the states and one is the actions. We'll discuss. And here if you take this state, we have to represent the initial state like this with the arrow mark representation, and we have to represent the final state with double circle. And one more thing, this is the transition function. The arrow mark represents the transition function. Transition function. So the transition function is from current state to next state. We can say that it is a current state and we can say that it is a next state. So here we have to initialize the state with like this arrow mark representation. Starting state should be represented as an arrow mark like this, and final state we have to represent in the double circle. And this is about the graphical representation. And next one is about the table. So table, so here this graph we have to convert into a tabular form. So the table, how it look like, see here we have rows and columns. So here rows and columns we have. So this column represent input symbols, and these rows represent states. So these are, and this in this here we can represent it as a transition function. So the transition function should be represented in the delta form. Okay, this is the symbol we have to represent the transition function. So here this transition function is a combination of q cross sigma tends to next state. So here the Q which contains set of finite states and a sigma which we already discussed this alphabets. So which are like, if you take binary, it is like 0 and 1. We have the symbols 0 and 1. And this is about the table. So in the table we have two things. One is rows is represented as the states. How many states we have in the diagram? We can represent all the states in this rows. And we have the input symbols. What are the alpha sigma contains the symbols? We have to represent that in the columns. And this is the next state. So every field is filled with the next state. For current state to, this is the input symbol, and for current state, every time current state for taking one input symbol, it leads to the next state. This is about the table representation and mathematical function. So here this table is converted to mathematical function, like it's a transition of current state, comma, input symbol which is leads to next state. So this is the mathematical functions, that is the transition functions for every state. So for every state we have to give an input symbol and it leads to the next state. So we'll discuss clearly in the next slides. And this is about the representation of finite automata. We have three types of representation. So one is the graphical representation, and second one is the tabular representation, and third one is the mathematical function or transition function. And next, so here we already discussed that finite automata without output and with output. So with output we have Moore and Millet. And next, without output, we have a deterministic finite automata and non-deterministic finite automata. One more thing is also there, epsilon NFA. So before going to all the things, first we have to discuss about the discriminate finite automata. So discriminate finite automata, the machine can exist in only one state at any given time. So this is the main thing. So, and if you observe that non-deterministic finite automata can exist in multiple states, and this is the only one state, and the non-deterministic finite automata is a multiple states at the same time. So this is how we'll see this with the diagrams. So for DFA, so if you take the transition diagram, we have so state initializing this one, and after that we have final state, so which is represented in the double circle, and this is the action which is performed with the input symbol. So here we have taken, so alpha is equal sigma which contains 0, 1. Yes. So this is the alpha sigma symbols. We have two symbols 0 and 1. And here this is the DFA. So only one state at any given time. So only one state. So if you give as an input current state Q naught, if you give to this current state Q naught, it leads to the next state QF. Only one state. So DFA which contains only one state at a given time. And we also observe that NFA. And here as usual we are initiating the state with the arrow mark representation. After that we have final state, and also we have one more state intermediate state we can say. So for the same input symbol, we are having the two states. That is the main difference in the DFA and NFA. So DFA, it leads to only one state, and here it is in NFA, it is leads to two more states, two or more states, multiple states. We can say that multiple states. So this is the main difference. And one more thing, epsilon NFA. So NFA, for this we have to extend the epsilon symbol. So same thing Q naught. So for epsilon input symbol also we can leads to different states. So this is the main difference between the discriminate finite automata, non-discriminate finite automata and epsilon NFA. And next, so here the language, which language is going to be recognized by this DFA? So the deterministic finite automata, some languages only recognized. So what are those languages? We'll see. So here the let LA, so the language which is represented in the form of L notation. So and A, be a language recognized by a DFA. And this is called as regular language. The language which are recognized by the DFA is called the regular languages. And we'll see the location where this language is located in the Chomsky hierarchy. So here is the overall computation, theory of computation which deals this a formal language, and this is the hierarchy. So in this we have the initial regular languages. We can say that it is a type 3 language. So in further videos, we can also describe this, what is meant by type 3 language, type 2 language, and type 2 language, and type 1 language, and type 0 language. These are all the languages, formal languages, which are described by the Chomsky hierarchy. So here, where is it located in the sense? It is a regular, so which is a basic thing which is located near the context-free grammars. So here the regular languages, those are represented in the bold form, that is blue color. So that is the language which was represented, which was recognized by the DFA. And coming to the definition, so what it contains. So till now we have discussed what is DFA and what is NFA, how it is differentiating from DFA to NFA. So now we will discuss about the definition. So the definition which contained, it is a phi tuple. So which contains a phi tuple. So what it contains in the sense of, in phi tuple, the Q. So Q is nothing but a finite set of states. So finite set of states. In diagram, if you see the diagrams, transition diagram, so how many states we are representing in the diagram, that should be noted in the Q, capital Q. Like this. And next, we already discussed this symbol. It is a sigma which contains the alphabets. Which alphabets? If you take a binary, we'll like write it as a flower basis. In middle, we represent 0 and 1. And next, Q naught. So initializing, whenever you are going to initialize the state, that initializing represented with the arrow mark, that is going to be stated like Q naught. So usually we'll represent initial state with the Q naught only. And F, so finite set of state, accepting states. We can say that it is a accepting states, finite set of accepting state. And it is, next one is about the transition function, which is represented as a delta. So delta, which notes that a transition function which is mapping between the Q cross sigma. So Q, here we have multiple states which are all involved in this diagram. So Q naught, which contains Q naught and QF. Not only these two, we based on the construction of DFA will represent more multiple states we need. For every state, we have to multiply with the every input symbol. Like here, I have taken only the binary digits, so 0 and 1. So 0 and 1 I am taking as an sigma. So in that sigma, how many symbols we have? So every state is going to be connected with the every input symbol, which leads to the next state. So Q is also which contains the states, next states. So this is the overall transition function, and we'll represent this phi tuple in the form of like this. Q is a finite set of states, and the sigma which contains the alphabets, and Q naught is the initial state, and F is a set of finite accepting state, and the delta is the transition function. So whenever asked for the DFA definition, we have to represent this phi tuple every time. And next, so what does a DFA do on reading an input string? So what will happen after giving the input, string to the DFA machine? What will happen? So for that input we have to give a word. So the reading an input string. So the string which is going to be given as an input to the machine DFA. And we can say that string is also called as word here, W, and the question is W is acceptable by DFA. So W is acceptable by DFA. So this string, which is the string is given to the DFA, is it acceptable by this DFA or not? We have to check. So if it is accepting, we have to give the accepting state, and if it is rejecting, we have to give it to the rejecting state. So what are the steps involved in this DFA construction? We'll see. So first, start at the start state. So previously we discussed about the graphical representation. So in that graphical representation, we initiated with the symbol Q naught like this. And next, we have to start like this. And for every input symbol in the sequence W. So here we are taking this W as a word. So in this word we have the string. Suppose example, we have 0, 1, 0. So this is the word or the string. We can say that a string. So this string is going to be given for the DFA. So this string is going to be given for the DFA. What will happen? So here for every input symbol in the sequence, W do. So for every input symbol, we have to give it to the sequence and compute the next state from the current state. So compute the next state from the current state. So here, if you take this as a transition diagram, so here every time initializing like this and final state is represented in the double circle. So compute the next state. So every state is giving the input symbol and which leads to the next state. So that is how for every input symbol we have to give the next state's representation. And if after all symbols in W are consumed, after finishing all these 0 finished and 1 finished and 0 finished, after consuming all the input symbols in the string, the current state which leads to final state or reject state. So if it is reaching the final state, the string is going to be accepted with the DFA, and if it is reaching the final rejected state, it is not not recognized by the DFA. So that is how. So otherwise the reject W. These are the steps involved in the DFA construction, and we'll see with the example how it is going to be constructed with the DFA. And if you observe this, we will give the language. We will give the one language, not a specific string. We will give one language to the DFA. We have to construct a DFA for the given language. So previously we discussed the regular languages we are giving to the DFA. So here what kind of language we will construct a DFA for this one, we'll see. So here is an example. So to build a DFA for the following language, so here the language is given with some condition. So what the condition? So W is a binary string. So binary which contains the sigma 0, 1. 0, 1. So here the binary string that contains 0, 1 as a substring. So 0, 1 as a substring. We are telling that the 0, 1 should be there in the string. So for this we have to construct a DFA. And for that one, what are the steps involved and what are the criteria we need for this construction of DSA, we'll see. And what are the steps involved. So first, as we discussed that it is a binary string. So the sigma contains a 0 and 1. And next step, decide the states. Q we have to decide. So how many states required for this language we have to represent in the form of capital Q. So previously in the definition we discussed that it is having a 5 tuple notation. So in the 5 tuple notation, first one is about the finite set of states. So Q is a finite set of states which contain all the states required for this DFA construction. And next one, designate start state and final state. So we have to, what is the initializing state and what is the final state we have to decide. And next one, transition function. So these are all the things we have to find before construction of DFA. And final states, same as accepting states. And next one, non-accepting state. Other states as represented as a non-accepting states. In the middle intermediate, we have, if suppose it is the initial state and this is the Q1 is the next state, and so this is the final state. So this is called as, if it is, this is an accepting state and this is a non-accepting state. Non-accepting state. So accepting state and non-accepting state. So this is the steps involved in the construction of DFA. And next, how we have to construct a DFA, we'll see. So DFA for the strings containing 0 and 1. So there is a condition in the language, the string going to be start or not. There is no condition like starting and ending. So this is the substring. So substring we need to place in every string. So substring should be 0, 0 and 1. It is a sequence, not a 0 and 1. It is a sequence of 0, 0, 1. So here we have to elaborate the language like this. So the string which contains the substring 0, 1. So substring, so this is the minimal thing. So every substring first we have to write. After that we have the sigma values 0, 1. So the substring going to be start with either 0 or 1. So the starting of the symbols is 0, 1. How many symbols we have? 0, 1 symbols. So I am starting the string with the 0 and 1. The substring is common. So the string going to be start with either 0, 1. And next one, and here we have seen the starting and next ending. So the substring is ending with 0 and ending with 1. So this is one combination. So we have to find out all the possibilities of this language by forming this condition with the language which is formed by this condition. And next, and we also have the criteria like the starting and ending. Yes. So the substring is in the middle. And it is also starts and end with the zeros. So like this we have to elaborate all the language of strings possibilities like this and so on. There is no ending. And here we have to, first step what we have to do is we have to initiate the start state. The first step is the start state. How we have to represent it? It is like this. So here we have to represent in the start state, and initializing the state is called as Q0. We already discussed. And next, so here before construction of this DFA, we need to first identify the minimal string and maximum string. So maximum string. So what is the minimum string? So minimum string is nothing but here 0, 1. And maximum strings, which is either starting and ending with 0, 1, and we can represent in the middle of the string. The substring is in the middle of the string. So here, this first we have to find the minimal string combination for the DFA. So first, before for that one, we have to initialize the state with Q naught. After that, we have to consume the input. The second step in the construction of DFA is we have to read all the input symbol in the string. So first symbol is about the 0. So whenever we have to give the input to the Q naught, where it is going. So Q1 is the next state. So for Q naught, when you give as an input 0 to the Q naught, it will leads to the next state Q1. And next, and one more string, I have finished 0, and after that 1 is there. Q1 we are giving the input to the 1, and it leads to the Q2. And so for this we have to, so after finishing this, either it leads to accepting state or rejecting state. So that I am stating the Q2 as a final state. Why? Because 0, 1 is already reached. This 0, 1. So if you give as an input to the DFA 0, 1, so it is after consuming these two inputs to the states, it is reaching the accepting state. So this is the minimal construction of DFA. And what about the maximum string construction? So here the string is going to be start with 0 and ending with 0. And here if you give as an input, if you take 0, 0, 1, so what will happen? 0 is there and 1 is there. And next, and 1 is there. And it is the starting with 1. What will happen? So 1 is there. So there is no 1 here. So from Q naught initializing, we have to represent here like this. For Q naught, we have to give as 1 as input, and it is also self loop like this 1, 1, 0, 1. How many ones are there? We can also represent with the self loop. How many ones are there in the string? So all will be solved by this single loop. And next, and what about the final? It is about the string is initialized with 1. And what about the string ending with the 0 or 1? And 0 and 1. So the string is either going to be end with 0 or 1. So this is how the infinite loop. So we are giving the loop. How many times we have zeros and how many ones after the substring. So that is solved by this self loop. And what about in the middle of substring? So we can also have 0, 1, 0. So and about 0, 1 is common here. And what about this 0? After 0 we have, so 1, 0, 1, 0, 1. 0, 1 is the substring, and we have going to be ended with 1 or 0 like this. And what about after 1, 0 is there and 0, 1 is there. What will happen? So if in the middle of we get two more zeros like this. So this is the substring and this is the string. So this string is going to be accepted by this DFA. How it is, we'll see. So here it's already there 0. If you have more zeros, we have to represent this self loop for the 0 Q1 0 as an input symbol. So this is, with this, every input string is going to be accepted by the DFA. So we'll check with the one more big number. So this is the substring, and fine. So it is a initially we have 2 ones and finally ending the zeros, 2 zeros. So how it is, we'll see. For this one, first step, first 1 is going to be self. So 1 is already there for the Q naught, where it is going to, Q naught is going to 1 only. And so self loop, self state. So Q naught comma 1. So Q naught comma 1, it is leading to Q naught only. And after that, there is a one more 1. So what will happen? One more one. So Q next state is also Q naught, and one more one is there, and next it is also going to the Q naught. So after that, giving next symbol is about the 0. So Q naught comma 0, where it is going? So Q1. So Q naught 0, where it is going? Q1. And next, and after this, Q naught, sorry, next state is a Q1, and Q1 comma 1, where it is going? Q1 comma 1, Q2. And next, Q2, so 0 as an input, Q2 comma 0, where it is going? Q2 only. And after that, Q2 comma 0, Q2 only. So after consuming all the input, all the string inputs, finally it is reaching the Q naught. So that is the final state. So this is how we have to construct a DFA for the substring 0, 1. And for initial slides, we represent the finite automata in the 3 forms. What are those in the sense? First is the graphical representation, so which contains the states and actions. And it is having the initial state like this and final state like this. They were circled. And initial state with the arrow mark representation. And second one is about the tabular representation. So tabular representation is like this. So here table, if you observe that we have to represent DFA with phi tuple. Phi tuple. So after construction of this DFA, we'll easily get that phi tuple. So phi tuple, we have Q and a sigma and initial state and final state, and next is a transition function. So delta is a transition function. So here what are the Q contains? Q contains the 3 states Q naught, Q1 and Q2. And next sigma contained, it is a binary representation of the language. So it contains 0, 0, 1. And next starting state, initializing the state is Q naught, and the final state only we have accepting state Q2 only. So final state F is Q naught, Q2 only. And the next transition. So transition function, which is represented in the form of table. So the table contains, which we already discussed, these 2 symbols are called as input symbols or alpha sigma symbols. In sigma, how many symbols we have that should be represented in these columns. And next, these are the states which we have. How many states? Q. How many states in the capital Q? Thus all the states should be there in the transition table. And in middle, so we can also represent this delta is a Q cross sigma, which leads to next state. So these are all the next states. So we'll see this one. So Q naught, we are taking the first initial state, and this initial state and final state in the tabular form, we have to represent initial state this arrow mark and final state with the star representation. This is the most important thing. And Q naught is the initial state. When we are giving the Q naught, and if you consume the 0 as an input to this one, so where it is going Q naught to 0, it is leads to the Q1. And next Q naught 1. So Q naught 1, where it is going? Q naught 1 self state, it is going to Q naught only. And next next it's already all input symbols are finished and for this state. And next state is about the Q1. So Q1 is having Q1 is also consumed 2 input symbols. So Q1 0, where it is going? It is going to the next state, self state. So Q, that is Q1. And next Q1, for Q1, what 1 is an input, where it is going? It's going to the final state, that is Q2. And next, these 2 input symbols are finished, and next state we have to take. So here the star mark representation is the final state. So final state Q naught, when we are giving the 0 as an input to the Q2, where it is going? Only self state Q2 only. And for the 1 input symbol also going to the Q2 only. So this is how we have to construct a DFA for the minimum string of 0, 1 substring. And one more thing, and the representation of the finite automata, we discussed like we have to graphical representation and tabular representation and mathematical representation. We'll see the third one about the mathematical representation for this given DFA. So mathematical representation, in the sense, here we already discussed the transition of states. So transition of states, here we have current state is a 0, q naught, and the input symbol, if you take input symbol 0, where it is going next state. So next state is about the q1. And next transition of q naught comma 1. So q naught comma 1, where it is going q naught comma 1, it is going q naught only. And next transition of q1 comma 0, so where it is going q1 only. And transition of q1 comma 1 as an input, and it is going to q2. And next transition of q2 comma 0, it is going to the state q2 only. And transition of q2 comma 1, where it is going q2 only. So these are all the mathematical or transition function, we can say that one. So this is the representation of transition function, that is mathematical function, and this is the graphical representation, and this is the tabular representation. So these are the three representations of the finite automata. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.